model for accelerating the performance of image in encryption using deep neural network and chaotic map. Welcome, ma'am. Over to you, ma'am.
Yeah, thank you, ma'am. Good afternoon, one and all present here. So, as ma'am told, so last day of our FDP. So, I would like to give my last work, like based upon this encryption and deep neural network. So here, it's a top title, as ma'am told, robust optimization of model for accelerating the performance of image encryption using deep neural network and chaotic. So here, I have included chaotic map also, along with deep neural network concept also. This is the outline of my presentation. So, starting with the proposed method. So here, as I told, deep neural network have used mainly to optimize the performance of the symbol encryption approaches. Sorry. And even I use chaotic map concept to enhance security. In all my work, you can see like I have used two types of algorithm to enhance security performance. And even the third stage is after finishing the encryption.
Ma'am, have
Yeah,
water, ma'am. Sorry to
yeah.
disturb.
Yeah. Thank you. So after finishing all this thing, we have to do the performance analysis. So we have done all the performance analysis as we have done for the previous works also. And I have proved that this algorithm is strong with respect to practical application, and it is going to resist against all the common attacks. So before starting, we should know what is autoencoder, right? Autoencoder. So what is stacked autoencoder? It's a neural network actually. I think all are aware of that, which is mainly composed of multiple layers of autoencoder. And even each layer, as I told, multiple layers are there. Each layer is trained on the output of the previous one. So layer by layer, each layer is trained by the output of the previous one. So that's the stacked autoencoder. Okay. So this allows the network to learn more complex representation of the input data. The stacking is mainly stacking of the autoencoder allows the network to learn more complex representation of the input data. So here I have used stacked autoencoder, okay, which is in deep neural network. So that what I have done is my input data is given to the first layer of input, which is trained, okay, it is learned and shared to the next layer. So it is each layer is trained on the output of the previous one. So it is trained, and final layer, I got the trained output. Okay. So this is my this is just the structure of the autoencoder I have mentioned here. So actually what they are doing here, input. Okay, suppose input is x means, okay, we have given x as a function. Okay, then this will do the calculation based upon the weight and the bias. Okay, weight into input plus the bias is given to as an output of the first layer, which is given to the input of the next layer. Okay, so right like that, we have trained layer by layer, and the final output we can use for encryption. So this is a proposed method or research methodology, I can say. Here, as every work, I have taken 0 to 55 error of pixel. Once again, I'm telling why I have taken 0 to 50 error of pixel. In the sense, each pixel contains, or each, if you take each pixel value, or it's a range from 0 to 55, right? So that is the reason I have taken 0 to 50. We can take any array of elements or any array of pixels, okay? For my convenience, I have taken 0 to 55 array of pixels. That is gone under conventional encryption. Then it is given to for a final encryption. Okay. So if you see this stack, SA is stacked autoencoder model. Okay. So if you see here, you can see in SA network model, input is the array of pixel and target is my encrypted data. So these both have given to get a SA model. So finally, the MEM SA model looks like this. So input is 0 to 55 array of pixels is given to the neurons, okay, which will be trained, okay, by with the help of weight and bias a secret key given to the next layer, again train, so and so. Finally, I'll get a final data, trained data, which is used for encryption. So here my secret key are here under conventional encryption, I'm using different method of encryption. Those all secret key will come, and in generating SA model, my weight and bias is my another secret key, right? And after the final output, what I'm getting is the encrypted data. Okay, so stack autoencoder model once again have highlighted here so that you easily can understand. So I have taken two stages of autoencoder. We can take multiple autoencoder. Okay, I have taken autoencoder 1 and autoencoder 2. So input is given to autoencoder 1, trained and given to autoencoder 2. So activation layer I have used a softmax. Okay, so activation layer is mainly used for normalizing, get the normalized data, and finally are getting the values. Okay, 0 to 55 locations you will get different values. Okay, so this is a the stack autoencoder model, how the calculation have been done. Input multiplied by the weight plus the bias. Okay, will give the output that is given to activation function tan sigmoid. This is again multiplied with input plus bias. Okay, again act. So this is like so on it will go. Okay, so this is final output after softmax layer activation. I'm getting the final output here. This all are the bias vector. So here I have used three different bias vector and three different weight as my secret key. The final sparse autoencoder connected diagram is like this with the equations I have mentioned here. So X input, W1, V1, weight and bias. So for that, the equation is like this. Okay, and the sigmoid, tan sigmoid is the activation function for the first layer. So H1 equal to, this H1 is equal to tan sigmoid of B1 plus W1 into X1. Okay, that is given to second. Second means again tan sigmoid I am using here B2 plus W2 into H1. Okay, this input taken as this output taken as input for a second layer. Then final Y is a softmax. Of course, softmax is the last like the end the activation function used is softmax. Okay, so B3 plus W3 into H2 is my Y. Okay, since it is three weight three bias coming, so I have used a 3 cross 3. So in the previous ANN, you might have observed 2 cross 2 because that is only two weight and two bias used. So here are three weight 3 bias, so 3 cross 3 matrix weight into the input into bias plus the input into weight plus bias will give my final output. So this is the calculation how it is going to happen. Okay. So now the encryption part is very simple. Has we seen all the work? Input image, okay, whose histogram like this. I have to get a DNN train model like this. DNN train model, okay, is used for DNN encryption. So what is happening? 0 to 55 pixel 0 to 55 locations. We can see this many number of pixel values, which is used for replacing the pixel values of the input image. And finally, I'm getting a encrypted image like this with a good histogram performance. Okay, and if you go with the conventional encryption flows, it is slightly different with respect to the previous work. Okay, so here also I have level 1 and level 2. That is confusion as well as diffusion is used. Here I have done the first level is simple only a permutation because permutation of combinations is like we can do with any secret key. You can the help of secret key we can just shuffle the data. Okay, or you can do Arnold scrambling or 3D cat scrambling. So many scramblings are available. Any type of scrambling you can use. Here, just for simplicity, I have used permutation of input image with the help of secret key only. In sub, you can change. And level 2, what I have done means I have used a combined sine and cosine chaotic map. Okay, the help of a 16 by secret key. Okay, this is a similar kind of algorithm we have discussed in second day. Okay, but not exactly same. Little changes are here. And with the help of 16 by secret key, okay, we are getting a final encrypted image like this. Okay, then we'll see how this combined sine and cosine chaotic map is done. Okay, this is second level of encryption. This combined sine and cosine chaotic map encryption. Okay, so what actually I've done is suppose this is my input image. Okay, of size 56 got 56. Convert the column vectors. I have taken all the column vector. Okay, into 8-bit binary. So each pixel carry if you can each pixel is an 8-bit binary, right? 88 convert it to binary, you will get like this. For example, again 88. So convert each pixel into binary. Okay, binary. So convert each pixel into 8-bit binary. So how like that? If you take on, I have taken only one column. Okay, like that, all the column you take and convert to binary. So that if you take this as one image, so I will get how many 8-bit plane. 8-bit plane of size m cross n. M cross n in the sense, suppose image size is m cross n means here also I can generate m cross n 8-bit plane of size matrix. Correct. So each column vector is converted into m cross n matrix. Okay, and each this column vector is converted into 8-bit plane of size m n cross n. So like one bit plane, second like that 8 plane of matrix we can get here. These 8 binary images, or we can call as 8-bit plane of or image or 8 binary images of n cross n, is what we have done is convert each binary into decimal. So what I have done, I have convert each binary into decimal and reshape to get the final encoded image M cross M. Okay, that is bit XORed with the 8 binary image of the M from the second level of encryption. So we have here bit XOR done with the chaotic sequence. How we have done, we have discussed in second day. So yeah, there also we can generate 8-bit binary sizes. Okay, that 8-bit binary image and this 8-bit binary images we have a bit XOR, and finally I'm getting a image which is converted into binary to decimal, and after reshaping I'm getting the final image M cross. So to get the 8-bit binary token, we have to do this calculation converting column to vector, and from the chaotic sequence, okay, we have to generate 8 binary images. Okay, both we have to bit XOR, and finally are getting the output image. So this is already we discussed this one, how to generate that ASCII key, right? ASCII key. So as I told, 16-byte ASCII key I have used here. Okay, so so what is the algorithm behind this? Is 16-byte ASCII key. I'm dividing into two, like 6 into 8, 6 into 8. Okay, because 1 byte is 8-bit, right? So 6 like that I'm divided like XY, and that is converted into an ASCII total of 48 bit, 6 8 a 48-bit binary. Okay, this is my the final key what I got from the 16-byte key. Okay. So this is equations behind this combined sine and cosine chaotic map. Cos AXN plus sine BXN. Okay. Now, this the remaining, I think we have discussed the same thing second day. After this calculations, okay, we will be getting X, Y, and A, B, like that, some 4 parameters we are getting, like initial conditions and control parameters, which are already discussed. And initial conditions and control parameters are another secret key, which can be used for second level of encryptions. Okay, so here I'll show you what are the keys we have used all together. So we have multiple keys used here to make our algorithm more strong. Actually. So if you go with the outcomes, okay, or the visual outcome of proposed system, so I have taken real-time images as that is both black and white and color. Okay, all have taken, and these are my the output I got. Decrypted image, encrypted image, all you can see, permitted image, grayscale image, and the original image. Okay, so we are doing permutation, that is confusion and diffusion, both output, then decrypted image also. After decryption, we are getting the same image exactly back. Okay, so this is a sample outcomes which I got in my proposed method, and even the result comparison is done in all the works. So has taken the same the set of 10 images: Lena, baboon, bird, dog, fruits, pepper, hat. Calculated the correlation coefficient across horizontal, vertical, and diagonal, and even the differential attack analysis like UAC and PCR, entropy, and even the time taken also considers. Okay, so, but time taken compared to AN is faster. So we got 0.2 like that only. Here it is compared to N. This is taking more time. Little time extra it is taking. And if you go with the the comparison, so result comparison I have done with some 6 paper. Okay, and these all are their values, their NPCR UACA value with respect to the proposed scheme. So horizontal, vertical, diagonal values we are getting less than 0 or 0.00 range. Entropy we are getting around 8, and the NPCR 99.87 and UACA I'm getting 33.61. Okay, I'll run the code and also show once all the values. And if you go with the results, the histogram and the correlation analysis of the different images, these are the output I got by using DNN. All the images with their histogram input, their encrypted output, the histogram of the encrypted output, correlation coefficient of horizontal, vertical, and diagonal, all have represented here. Okay, and have taken all the set of 10 images, and these are the results I got for all the images. Okay, and even real-time images have taken some 4 samples, and not only the which I got in the SAPIA database, real-time images taken and compared all the histogram of the input as well as the output, getting uniform response of histogram. And if you can see the correlation analysis, straight blue color represent the correlation of input image, and if you see the red dot is the correlation of the input image. This is fully scattered, which means there is no correlation between the neighboring pixels for an encrypted image. Okay, and even the same the real-time images that military, medical, that check all for those images have calculated the horizontal, vertical, and diagonal. Okay, so USC, NPCR, and entropy, and even the time taken also mentioned here. So if you go with the key space analysis, yeah, what all the keys have you seen? Input size is my key. The permutation key, as I told, for scrambling, you're using one secret key, 0 byte size. Bit level conversion, like we are converting bit like a 68 bit to 16 bit to 8. That conversion we are doing. For that, I'm using 1 byte secret key. Okay, and left time I'm shifting the bit, left time must be or right time must be, that also we can decide. Okay, so that is known to by the people who are doing coding on it. So I have a left time must be here. So for that I'm using 1 byte as a secret key. And for chaotic encryption, we have key 2. So this is external key I use for chaotic encryption. Then for if you go for stack or encoder, we have to use binary column, hidden size 1, hidden size 2. Okay, so all this are secret key used. So this and all in the code I have mentioned. And final key space is 110 byte. That is, if you go with bit is to 880 bits, right? So 2 raised to 880, which is large enough to resist brute force attack. So compared to all other algorithm, DNN key is more complicated and I made more complex. Okay, so the key space is very difficult or for the attacker to break. So that's why it is very large enough to resist a brute force attack I mentioned here. Okay, now if you go with the work like conclusion. So what I can say is here, have performed a unique mechanism, we can say, performing image security with a deep neural network. Why it is unique? Because here deep neural network is the second stage of encryption. Because there we are doing two level of training. The training is done, and after training, the trained value only we receive for encryption. Before that, the input is the encrypted output of the conventional. So conventional encryption we are doing. Followed conventional encryption is having two types of encryption. The confusion diffusion. After that, we are doing this one. So it's like more security is more. I'm performing image security with a hybrid mode of encryption. Okay, and it's not offering any heavy cryptographic operations because you can see the time taken is less actually. And also it's overcome the iterative problem of feed forward, because if you go with feed forward method in deep neural network, it brings many issues like iterative problem. Okay, so that is not happening here because I am just after like getting one layer of output, that is passed next layer of output, and immediately that result I'm taking. So there is no iterative problem I'm facing here. Okay, and numerical analysis have done and show better result, right, in contrast to the other frequently used machine learning approaches. And the key size is large here. Okay, this can resist the brute force attack. So this work I published in a Elsevier journal, and the previous work I have done published in IEEE Access also. So this is about this work. Now, as I did the similar type of method, like as I told, we are doing confusion diffusion, right? Then we are giving to neural network, whether it's ANN, then SPM machine learning, then DNN. So this all are similar, almost similar, right? So what I have done is I have done the comparison all three, all the values which I have got, like horizontal, vertical, diagonal, US, all the values for one particular Lena image I have taken all these values. Okay, the values. Okay, I have plotted here. So you can see here DNN. This is horizontal correlation value DNN, vertical correlation value, diagonal, and UA and CR. Okay, yeah, even the time taken. And even for AN and all have taken. Okay, so I have done some data like this analysis to prove that. Okay, this is a digital analysis sheet that just to prove which is giving better results. And I got DNS giving better results. How we have judged this is because I've given some weightage. Okay, I'm given 10 weightage for all, and the score also put actually. So how has I have put a score means here can see it down. 3 is good, 2 is average, 1 is low. So if it is good, is compared to the value 0.0019, 0026. Okay, this should be or original value should be lower the better. So lower value when vertical should be lower the better. And, uh, because usually minus one is again so again the and UACI here. So the 30.87 is good value. Okay, that is having 3 mark, and 32 is less than 33. 33 I'm giving 280, 2 mark. Okay, so like that, if we given the average good low value, okay, and if we add all the score, okay, if you add all the score, we are getting 180 for this DNN, 130 for ANN, and 140 for STM. So which implies that actually DNN is giving better result compared to the other algorithm like ANN and SPM. Okay, so just for comparison, I had to prove like which work is better compared to the other work. Okay, so that's about my work. So in all this work, I want to conclude and I had to tell the future scope so that somebody is doing interested in doing a research in this area. They also can think about it. So in all the work, like we had developed a neural network. All this last 3 work, neural network based system we have done. Why neural network based crypto system? In the sense because the crypto analyst or that cracker, okay, he should not only need the topology of NN and the key to crack system, but he should know the number of adapted iterations and the final weight of for the encryption and decryption system. So it is not easy for the attacker to get the information from my neural network because I have defined my neural network with different key, weight, bias, right? And even the iterations, how many times I'm training it. So that iteration is also not to be me only, right? So he should know number of adaptive iterations, the final weight also for the encryption decryption systems. Okay, not only the topology. Topology itself will not give. If you know, if my model is I have given public to all from my model, nobody can easily get the values, right? You should know the key. You should know the iterations. I should know the final weight, right? So that is a major concern here actually. New NN based crypto system, and even the circuit analysis for over the SVM, AN, and D and all method we have done, right? And he proved that it is all is resistant against the all attack. And performance wise, faster we conclude AN is better. Okay, so AN is better in the case of speed wise, but if you go with all other values, DNN is giving good result. And digital analysis of machine learning and neural network encryption scheme has been done, and we finally conclude DNN is giving the better result for digital analysis. Okay, and the thing is, this all the work I have done for only one image, right? Lena image, the baboon image, cat image. So this methodology can be extended with the training of multiple images for real-time application because that is still how I'm doing. Okay, so that you also can think how to train, how to take multiple images as an input. Okay, then to get a one data, and with that data, how we can encrypt a particular image. Hmm? So because different image give different features of information. With that information, how to train. So that is little complicated. Mine is very simple. I have taken only input array of pixels as well as one encrypted image by using conventional encryption method. But this way we can think okay in future and how to develop a more like sophisticated output so that we can encrypt this images. So that is the thing the future scope I have mentioned here. So that's about my work, ma'am, sir. So any doubt in this, you can ask. And parallelly, I'll just run and show the output. Um, Okay, input image histogram, conventional method, okay, encrypted, and histogram. Okay, so there I'm using combined sine and cosine charting map. Then DNN training. So this training has been done, and the train model also is coming now. Softmax layer also came. The final activation activated output. See softmax layer encoder, second encoder softmax layer. Okay. And I have done some iterations that you can change iterations. Okay, encode you can change. Okay, softmax layer output, encoder decoder output. Okay, then encryption. Yeah. So I'm getting black, fully black encrypted image. So I maybe have to change the value, some values, so that I can get somewhat like the same encrypted image also. Okay. Since it is pure black, I think performance analysis you can see encrypted image will be white because it's free of the see. Only input image I can see here. The correlation of white is black because this is full black, right? That is the reason. I'm getting here no red spot. If it is dot 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 means I can get that red spot here. So we'll see the value. Yeah. So I'm getting NPCR 99.6, UACA 33. Okay. And this correlation, why? Because I'm getting black. I mean, that's why NA coming because it's fully black. That is zero. So this is such. So any doubt in this, we can have anything if you want to discuss. We can have a discussion now.
Dear participants, please start.
Manikandan sir, any doubt you have?
Suppose anyone wants to work under so
Ma'am, I think your voice is breaking. I'm not able to.
if anyone so they to help, right?
Yes, ma'am. Can you repeat?
Can you hear, ma'am?
Yeah, it is clear.
Yeah. So our participants are there. So if suppose they are working under this topic, if they have any doubts, they can open to you, right?
Yes, ma'am.
Yes, ma'am. Okay. I think so far whatever you have explained, don't have any doubts. So your topics are very clear. So from day 1 to day 5, the workflow is very nice. Really, it was a wonderful sessions we had.
Thank you, ma'am.
The part of statistics. My side, actually, team members, this is Shamina, and this is Devamana and committee members for conducting this program and great success. And main success the researcher, I can understand that session. Great. So with they have job as a kind of schedule. Join the this will be generated as early as possible and will be program successful. Thank you.
Thank you all.
Thank you, ma'am. So
Thank
we
you.
can wind up with the session.
Yeah. Okay.
Thank you, Dr. Shima, ma'am.
Yeah. Thank you. Ma'am.
Thank you. Yeah, ma'am. Bye, ma'am.
Bye. Bye. Bye.